Question 5. Here we have the electricity question. We have a thermistor, which is a standard negative temperature coefficient thermistor, so as the temperature increases the resistance of it drops. We've got a variable resistor arranged in a straightforward series circuit. The resistor and thermistor in figure 4 make up a potential divider. Explain what's meant by a potential divider. Now there's a bit of exam technique here. What we shouldn't do is repeat the words of the question. So we really want to say that it divides the potential, but we can't because those two words have been used in the question. So we need to say that in different words. So a circuit which, instead of divides, I'm going to use splits. Instead of potential, I'm going to use voltage across two or more components. State and explain what happens to the voltmeter reading when the resistance of R is increased and the temperature is kept constant. So the temperature is kept constant, so this resistance will stay the same. If this is increased, then that will mean that the amount of voltage across it will increase. Why is that? Well, the potential is split in the same ratio. The potential of the supply here is split in the same ratio as the resistors of these. So if that one increases and that one stays the same, this one gets more potential than this one. If that one gets more, then that one gets less, because there's the same amount from the supply to divide up. So the answer is that it's going to reduce, and then we need to explain why that's the case. So it reduces. So that's the first thing, that's our state. Now we need to explain. T has a fixed resistance. As R increases, it takes a larger share of the total potential. So T gets a smaller share. Okay. State and explain what happens to the ammeter reading when the temperature of the thermistor increases. Well, I assume that they mean if this is fixed. So, as the temperature increases, the resistance of this then decreases according to this graph here. Because these two resistors are in series, the total resistance is going to be the sum of them both. The potential across the total circuit, the potential across the whole circuit remains fixed, so therefore if the resistance, the combined resistance reduces, then the ammeter reading will increase. So let's explain that. It will increase. Why? So that's the state. Now we've got to explain. As the temperature increases, the resistance of T reduces, so the total circuit resistance reduces. I is equal to V over R. If the resistance here reduces, the potential across the circuit stays the same, so I will increase. So current increases. Question 5.4. The battery has an EMF of 12.0 volts. At a temperature of 0 degrees Celsius, the resistance of the thermistor is 1.5 times 10 to the 3 ohms. The voltmeter is replaced by an alarm that sounds when the voltage across it exceeds 3 volts. Calculate the resistance R that will cause the alarm to sound when the temperature of the thermistor is lowered to 0. Right, we've got a lot of information here, so the first thing we do is we transfer that information onto the diagram. So the supply voltage is 12.0 volts. The resistance of this is 2,500 ohms. The voltage across this, when we're interested in it, is going to be 3.0 volts. And we can work out the voltage across this straight away. If there's 12 volts in total, 3 volts across that, then that must be 9.0 volts, because those two have to add up to that one. Right. Let us use the equation I is equal to V divided by R for the thermistor. I is equal to 3 divided by its resistance, which is 2,500. 3 divided by 2,500 gives us 1.2 times 10 to the minus 3 amps, or 1.2 milliamps. And then for the variable resistor, we just use V equals IR again, or R is equal to V over I, which in this case the voltage across the variable resistor is 9 volts. The current going through it, well, let's write on here, once we've worked that out, the current is 1.2 times 10 to the minus 3 amps. So that current has to flow through that as well. So that's 1.2 times 10 to the minus 3. So we do 9 divided by, answer is equal to 7,500 ohms. And that's 2SF anyway. Right, you could have used the potential divider equation there. You get the same answer, obviously. I think that that one is a really easy way of doing it. Question 5.5. State one change that you make to the circuit so that instead of the alarm coming on when the temperature falls, it comes on when the temperature rises above a certain value. So, as the potential is falling across this component here, the potential is rising across this component here. So if we just move the sensor from this component to this component, it will work. So move the sensor from T to R. Another way you could do it is by having a thermistor which increases in its resistance according to temperature, rather than decreases. But this is the simplest way. Just switch these two around, the sensor around.